Welcome everybody to our seminar. Today we have with us Orlagh, who is also a member of the seminar commission, and I'm sure you already know her. She did her PhD under the supervision of Juan Antonio Belmonte and Sebastián Jiménez, and while she was doing it within the University of La Laguna framework, she was working in the High Altitude Observatory in Boulder. Her PhD was on mainly solar physics, but also some on stellar physics. And she did her dissertation on March 2008. Since April 2008, she has been a postdoc here at the AAC, working mainly on stellar structure, evolution, and asteroseismology. And at the moment, she is still working on the same topics and co-organizing the next winter school, the 22nd edition, which is going to be on asteroseismology, just so you know. And with no further delay, I'll leave you with Orlagh.
Thank you very much for the introduction, and thank you for allowing me to speak today. Seminar commission. Okay, well today, for those of you who haven't read the abstract, which I know kind of just delete, general overview. There is a new telescope going to be installed on the Observatorio del Teide. It's a 1 meter telescope, robotic, automatic, and it's going to be equipped with a spectrograph for very high precision radial-velocity measurements. So this is what I'm going to talk basically about today, and details. As the outline is, well, the concept and the scientific goals, and I will probably spend about half of the talk talking about the science part, in particular my science. The rest of the talk I'll talk about the instrument itself, and so the information that you may need to know in case you want to propose something, and about the organization and scheduling of the observations and how the IAC is actually involved in it. Okay, so this is the mission statement. I'm going to read the slide. This is the only slide I will read. So the Stellar Observations Network Group is an initiative to design and build a global network of small telescopes. The goal of SONG is to become a key facility in both asteroseismology and planet search research programs, a facility that provides state-of-the-art data of quality that could not be achieved by use of any other space-based or ground-based facility. So that's the mission statement. In practice, SONG is proposed to be a network of 8 telescopes to a global distribution around the world to provide very long, nearly continuous observations, ultra-precise Doppler velocity measurements, so meter per second precision we're talking about, but there's also going to be precise photometry of faint stars in crowded fields. So SONG, I imagine this is where the name actually came from, is GONG. I think it was kind of a copy. So GONG is the Global Oscillations Network Group, which is a network of 6 telescopes to study the seismology of the sun. So it's an American-funded project. They built 6 containers like this, shipped to 6 places in the world, and this is the one that is up at the observatory. Okay. So from the SONG telescope, you'll actually be able to see the GONG container. So the scientific goals of SONG, asteroseismology, which is the part I am most excited about, so I will talk most about that, using radial velocity observations. Also characterization of extrasolar planetary systems, so radial velocity and gravitational microlensing. And then there's additional science, so this is where the IIC people should get involved, or in any of the other. So one slide about exoplanets, because I'd rather the experts talk about that. In radial velocity, we're going to look for low-mass planets in short-period orbits, the gravitational microlensing, characterization of statistics of planetary systems. And I'm not going to go into any more detail on that, because I try to stick to the topic that I'm most familiar with. So asteroseismology. In case you were here last week at Katrine Utterhoven's talk, but don't worry, we're not going to say the same things. We have about 2 slides, or 2 figures that overlap a little bit, but we're talking about different types of stars and different physics that we can learn. So asteroseismology is a study of stellar oscillations using stellar interiors using stellar oscillations. So it's very easy to determine oscillation frequencies with high precision once you have a long continuous data set. But these frequencies are sensitive to the structure of the star. So the evolutionary states, which define the structure and rotation, and any of the physical details in the interior. And the mode amplitudes that relate to the damping rate of the signal, they're sensitive to the near surface physics, so convection. So the main goals are to, fourfold. Depending on what you know about the star, depends on what you can actually do with it. So I would say that one of the first things that we can do, and we have been doing, is determining global stellar properties with very good accuracy. So you're talking about getting radii precision of 1 or 2%, masses to the same 1 or 2%, ages to less than 10%, even better. Now, you can't do this for very many stars if they're not in binary systems or multiple systems or in clusters, but this you can do with single field stars. So this is already is a first great step for astrophysics. Once we know a little bit more about the star, so in particular for stars that are a little bit closer, you can investigate things about the interior of the star, so the internal structure and dynamics. Once we know that well, we aim to improve our understanding of stellar physics and improving modeling. So this is one of the figures that Kathleen showed last week, the observational HR diagram. These are all groups of pulsating stars characterized by temperature, luminosity, mass, age, excitation mechanism of the pulsations, and the type of frequencies that you will be able to see. So the idea of song is to concentrate here, solar type oscillations. But you also find solar-like oscillations in red giants as well. So what I mean by solar-like oscillations is that these stars generally have broad convective envelopes, and it's here you've got all the convection that excites the resonant modes. So this gives rise to a broad spectrum of oscillation frequencies that you can use to characterize the star. Okay, so once you have your time series, as long as possible, you could do your power spectrum or whatever your favorite method of doing it is. So here's frequency, and this is velocity or power or amplitude, whatever you use to measure. So this is from 1980. This is one of the first oscillation spectra of the sun. And please correct me, was this one actually taken in Oceania or in Antarctica? I know there was a similar one at the same time. A similar one. Okay, so it looked like this. Now, 30 years later, and a lot of development of instrumentation, and et cetera, this is what we see for other stars. Okay, so here we've got frequency, again, on the x-axis, and power, or whatever your unit is on the y-axis. So here's the sun. And these are all power spectra of different stars. So what the first thing you'll see is that this acoustic power is in different frequency ranges. Okay? So basically, as your acoustic cavity changes, the range of frequencies that you're going to see is going to change. So in general, as your acoustic cavity gets bigger, so either your mass, it's a bigger mass, or your star is evolving, for example, the power is going to shift longer periods, or smaller frequencies. So these are we say main sequence stars. Now, more recently, from the space, using core observation, and this very nice figure as well, in Nature paper. So this is the frequency range. If I just push back a little bit, we're talking about this range here. Okay. So for giants, you have again this shifting acoustic power. But not only the shifting acoustic power, what you can see very clearly is as your frequency, as your power gets lower, so as your star is bigger, for example, the amplitude is much larger. So you've got 200 picrometers squared here, for example, and here you're going down to 5. Okay. So we're already learning like basic things just by looking at the frequency spectrum of these stars, and that's without going into any details. So we have, on one side, I showed main sequence stars, and I also showed this other type, the red giants. So the red giants you can do very easily with photometry. The main sequence stars, they're more difficult to do, but you can do them quite well from the ground, which is the idea of what we have song, the idea we have song. So generally the difference, from the ground you can get radial velocities, you can get amplitudes of meters per second, so you can detect these oscillations. They're sensitive to modes, low modes, one of the characteristics of the wave, of the propagating wave. But unfortunately you can only observe one star at a time. Meanwhile, from intensity, you have amplitude typically of a few parts per million, but you're sensitive to less modes. You can observe many stars simultaneously, but unfortunately from the ground, you can't do that, okay, because of the scintillation in the atmosphere. In any case, if you want to observe solar oscillations, what we need are continuous observations over weeks or months. So you can do it from space, and of course we're only really going to do intensity. I think there is a mission that is being proposed that will a spectrograph up there. Again, you're going to look at one star. Or you can look at observations from ground-based networks, radial velocities. This is what SONG is going to be. And just to show you the difference between what you can expect from photometry and radial velocities, these are two instruments on board the SOHO telescope, Golf and Virgo. Virgo is photometry basically, and radial velocity, and you can see there's a huge difference in the noise level, and this is why really radial velocity measurements are what we want. If we want to detect these frequencies that are much further down here, we really want to get to radial velocity. So although we can detect these frequencies, ideally if we have all these observations, we also need to know a little bit about what type of frequency it is. So what's the spatial characteristic of the wave? So very briefly, we use three numbers to describe them. We use spherical harmonics. The degree L, which is what I mentioned in the last slide, and the azimuthal order M. Both of these describe the surface pattern, basically on the star. If there's no rotation, we will only have these type of logo lines. Then the last one, the last number is called the radial order, which is basically the number of nodes between the center of the star and the surface. Okay, so the overtones of the frequencies, for example. Okay, so if we look again at this solar power spectrum, here you have, this is the frequencies again. Each of these corresponds to 1 degree, one of the spatial characteristics, and each of the radial overtones. Now the splitting value, you can see it, but I'm not going to talk about it. But it depends on rotation, and these stars are very, very slow rotators, at least for people who look at stellar pulsations, they are very slow rotators. So we can ignore this just for the moment, and this is another part of the physics you can look at later on. So we're just looking at the two numbers. Now because you see this very nice pattern, it's easy, more or less, to identify the modes, which is one of the main problems that you have for other types of pulsators. You might detect one frequency, two frequencies, three frequencies, and you don't know what it is. And this is a big problem that Katrine was talking about last week, and this is stuff that she's working on. Now this regular pattern we call delta nu. It's proportional based to the span speed across the star. It's going to give you an average value of the density of the star. If you look in a little bit closer detail, you have also this second regular spacing here, 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 and this is sensitive to the sensitive gradient in the core, or sensitive gradient, and of course in the core this is going to be much higher. So it's basically the core conditions is what will give you these numbers. So it's more sensitive to things like the evolutionary state. Now if you plot these two figures, the small versus the large, on what we call a JCD diagram, so which is Jan Christensen Dalsgaard, which is one of a major researcher in this field. He was the first one to propose this diagram. If we do it for a whole range of masses and a whole range of evolutionary stages or ages, you can basically see, you can get a rough idea just by using those two characteristic seismic diagnostics what the mass and the age of the star could be. So for example, if we put the sun, we get a 1 solar mass. Yes, that's it. And then we have alpha A and alpha B, they're closest, is the closest binary that we can actually observe. And they both have oscillation spectra, and they fit nicely onto this diagram. There's a little bit of calibration gone into that diagram. You know, sometimes I get a 1.05 solar mass star for the sun. So if we go back, to the figure, and if we split, we use this large frequency separation, and we just cut it into chunks, okay? And then we just stack the frequencies on top of each other. We could get something like this called a Michel diagram. So here on the x-axis we got reduced frequency, which is the frequency modulo this average large frequency separation. And these are the individual frequencies. And you can see that they kind of line up nicely. Okay, so in the asymptotic regime, we know that this is proportional to the density of the star. We can estimate the radius if we know something else about the temperature, the log velocity. But what we're also very interested in is the parts that are not in this asymptotic regime. The parts that deviate. Because these are things are going to tell us about the deviations from the global structure of the star. So things like where you've got sharp changes, the convective core, the transition region between the radiation zone, the convection zone, things like that. So this is the stuff that's, I think, is really exciting. Anyway, so just as an example, if we take the oscillation frequencies, but we don't use them themselves, we use this combination of frequencies, we can reconstruct the signal. And this signal we can decompose into, well, there's three basically oscillation signals, and they're related to the convection zone. So the two helium ionization zones and the base of the convection zone here. So when you've got data of solar quality, you can do this, and you can do a beautiful fit, and basically you can determine the position of the base of the convection zone, the mass helium in the convection region, for example. Now, if we do this for the stars that we hope we can observe, so the closest stars. So let's imagine we have two nodes working, and we're looking at one star for 4 months. These are the error bars, the simulated error bars that we put on them here. And you can see, well, you can do a pretty good job of reproducing most of this signal. So you can really constrain these three key physical ingredients pretty well. How about the convective core? So this is an example. This is a model. Some models. So 1.3 solar mass model. This is the radius from the core. So 0.2 values of the radius. This is the sound speed. So for the youngest, 1.3 until the oldest. So we're just going in steps. So here, for example, we probably don't have a convective core. Well, maybe. But as the star evolves, you can see that it develops a convective core, which gives rise to this jump in the sound speed. So the convective core will actually grow, and then it will shrink again. But while it is growing and shrinking, the jump is much more obvious. So this is going to affect the oscillation frequencies, and you should be able to see this. So another diagnostic using oscillation frequencies is using this combination of frequencies from the Cunha Metcalfe paper. So for these same models, we're going from 0.25 all the way down to 5.25 beta years. You have this value here. And adding in some error bars, you can see that we can observe this here. And with these error bars, we can more or less distinguish. We can say something about the size of the jump, for example, in the convective core, or the size of the convective core. And I think for the moment that's all I'm going to say about. One more thing, okay. A little bit about the rotation. So when the star rotates, these degrees, the L degrees, they split basically into, depending on the degree, 2L plus 1 rotation. So this is an example. So this is an L equal 1, and it's split into three components. This is an L equal 2, and we'll split into 5. Now the 5 components, the visibility of these components depends on the inclination angle of the star. Okay? So what you can do this is either you can determine the inclination of the star or constrain it very well just by measuring these rotational splitting. Or, well, for example, if you know the inclination of the star is 70 and somebody says it's detected the planet, well, you can say, no, you can't detect the inclination is wrong. But also, if you can determine the inclination of the star, you can measure the sin I, you can get the radius, the period, you can get the rotation rate of the star. So let's just move on a little bit to the part that maybe you possibly may be more interested in. So the song instrument and the prototype. So here is the Stare telescope. Is it here is or here was? It still is. Okay. Very soon it's going to disappear. This is where the song container is actually going to go. So they're going to be building a base here over the summer, and then the telescope, the container should come by spring next year, and then by summer we should have observations. Just quickly, we have the base. This is what it's going to look like. The container will go here, the telescope, the house, the dome, and then it's going to look like this. It has song written. You know what it is. So inside the telescope, we have a 1 meter, so 1 meter mirror. With an azimuth instrumentation. So you've got 2 foci. This foci at the moment, focus is free. So anybody who's interested in proposing something interesting, this is completely free. So the light will go through this focus, and this is where we have the dual color looking imaging. We have a telescope focus monitor with a filter wheel with 6 positions on it, and the entrance to the Creevey pot. And there's also an auxiliary port down here. So the reason there's an auxiliary port is because if people want it's basically for somebody else to propose other types of science on it. So because the characteristics of the camera, the most important things are you're going to see 0.09 arcseconds per pixel, 512 by 512. So somebody who may be interested in putting a different camera can use the auxiliary port for some good quantum efficiency, and basically the lucky imaging, well, it's going to be the visible and the red, and it's basically about 650 nanometers. Just to show the lucky imaging, the testing of it. So this is tested on the 1.5, again 1.5 meter in Australia. This is just focus on these 2. This is using 100% of the images, and this is selecting the best 5% of the images. So you can see you can really get good spatial resolution result. The spectrograph, basically it's going to be between 60,000 and 120,000. Depending on the width, of course, you can decide what you want to do. So between 6, you can vary. These are some of the characteristics. If anybody wants to look in more detail of it, all the presentations are available, or I can try to point you towards the right direction. The total throughput. So this is the footage for this here, and this is going to be what's going to go to the spectrograph, basically. Okay. So you've got the big iodine region here. So obviously, if you want to do things like abundances or something like that, but you can move the iodine region, the cell. You can just take it away. But this is basically optimized for radial velocity observation, so we probably don't want to do that. These are basically the 2 visible bands for the looking imaging. So you can come to the broad range. And the precision, which is one of the characteristics people will be most important in that. If they want to go, this is the magnitude of the star, this is the velocity precision for a 55-second exposure, 1.5 for with half mass, air mass, with a resolution of 120,000. You can see for a V equals 2 magnitude star, we'll be able to get a precision of 1 meter. Okay, so we're aiming at these very low magnitudes, so 1 meter telescope. We're aiming at bright stars, and with bright stars you can characterize them with other types of things like interferometry. You can measure the radii, you can get excellent photometry underneath. It's a different regime of science than looking at what the space missions look at, for example. So if you were interested in proposing for something, basically you propose it. If you get the time, you will get back just the radial velocity data. So the software has already been developed and it's been tested. And it's been tested on the alpha Centauri asteroseismology data from this paper here. So the red is what this paper actually publishes, and the black voids show what the current reduction software actually does. So you can see that there's excellent agreement between the two, so you can trust what you're going to get. So the proposed sites are, well, ideally, you're going to have 4 telescopes in the north, 4 in the south, even more if possible. The first one is in East Anya, and it's summertime next year. It should be up there and running, or testing at least. The next one is actually going to be there. The funding has already been secured for this. So this was actually an idea that has been going around for a long time, and they've been developing this. They got the money to fund the prototype, and partially from Carlsberg, Carlsberg, to support them. And they were discussing, this time last year, they were at a meeting, and they were discussing the funding opportunities, and they were going around different people from different countries saying, well, in our country it's bad, blah, blah, blah. Okay, this is where we are now. 1 year later, China is already they're building a node there. The US, well, they probably put it near in Hawaii. And they're waiting for a result. They sent in a proposal for 2 telescopes. It was reviewed very positively, but they didn't get it, but they were encouraged to resubmit for 1 telescope, and they did that about a month ago, so they're waiting now. The chances are there's going to be 3 nodes within the next couple of years. Okay. So how is it going to be organized, and where the IIT going to be involved? Okay, so because it's going to be a network, it's going to get complicated. But not only a network, but there's going to be a lot of different groups involved. So the definitions and everything has to be very clear from the beginning. So there's going to be a song steering committee, and anybody who puts something in, for example, the IAC, they're going to actually have the telescope, and they're putting money into build the base. They're going to be on the steering committee. And the steering committee are going to define, like, the terms of reference, the strategies for time allocation, and everything. So they're always going to have a top voice. So anybody else who really, really wants something, you should talk to the person who's not me or Pei or whoever is here, and we have a voice. So there will be one person responsible for each of us. So this is going to have to be decided. These are not decided yet. There will be a meeting coming up soon, and how to organize the observations is something that needs to be talked about. So apart from some key projects, so asteroseismology and extrasolar planets, you have some specific projects. So ideally, when you have the network, you might have some specific projects to use the full network. Or you can have your local project just use one single node. So anyone here at the IAC can propose something for these. But what you need to remember is you're only going to get a good review of your proposal if this telescope is what you need. Okay, so you need duty cycles, you need real-time requirements, you need length of observations, total length. This specific instrument, which is equipped with very precise radio velocity measurements, targets of opportunities surveys. If you propose something you can do with some other telescopes, you're not going to get it, obviously. But so yeah, we'll focus on basically what you can do with this telescope and not what you can do with another telescope. Ideally, the way it will work is there will be maybe a couple of months dedicated to asteroseismology, because you really do not want to interrupt it. You need uninterrupted time series. Then there will be a couple of months dedicated to exoplanets, and maybe one of the nodes can be working using a local project, for example. And it will work in blocks like this. And here you've got the targets of opportunities. So this is the ideal way it's going to work. So in order to get the time allocation committee working, or the strategies working, they need to build a simulator. So what they want actually from all of the community, including people from the IIC, is that they send in test proposals. And we're talking about soon, because I think in 2 weeks there is actually going to be a meeting where they're going to start discussing the type of proposal. So they want to hear from everybody else. What else do we do with this telescope? They want to include it, because they want SONG to be very unique and produce great science. But again, you're going to have to think about these are the requirements that they're looking for. So once, yeah, so I guess that's it. Mainly to summarize about the IAC and the song involvement. So at the moment, like, it's a major partner of this network. Okay, so it's not like we're just letting somebody put a telescope there and somebody might be involved in collaborating. It's active participation. So between INC and SOM, well, at the moment, because we're the people most involved with this type of science, and with these people, from Denmark, the University of Aarhus and the University of Copenhagen. These are the main people who put in the funding. This is a group, so the solar Earth. Does that stand for seismology? Stellar seismology, extrasolar planets. Basically, so we're the group behind it, first of all. So the benefits of the ISC are, well, we're going to be a full partner, which means that we're going to be part of the steering committee and, of course, the time allocation committee. But also, the instrumental telescope you put here means we're actually going to own a third of it. Other possible benefits, well, there's going to be a lot of collaboration for students, at least to Denmark at the beginning. And this is great publicity, of course, for the observatory. So what did the IAC promise on? Well, first of all, they're spending some money. They're building the base. They're going to make sure the operations run smoothly. They're going to maintain it. And these specific details are being finalized now with the memorandum of understanding. But to give you an example, the American Gong project takes about 30 minutes per week to maintain it. It's a robotic, automatic telescope. So they're kind of looking at maybe 20 minutes an hour. Obviously, in the first few months, they're going to take a little bit more. And get some training and maintaining some specific aspects. And finally, yeah, until the day one, well, the people you should come to are anybody from Sopere, Juan Antonio, me, Brandon, Hans, the lead, those people. So the ISP group, so we really should try and get involved, okay? So far, there's been an email sent out to a few specific groups, so we thought that maybe these would be more interested. So many people have shown interest. Carlos Lázaro, from Binaries, for example, NME, Paye with Earthshine. Is it Earthshine that you're interested in? Which one? I just mentioned you. You showed an interest in song. Is it Earthshine? Oh, sorry. Antonio, you're here. Sorry, Antonio. Artemio, Massive Stars, Gary, and Alex Oscar. These are people who showed interest. So we really encourage you to please think about it, propose things, because you really can, this is going to be state-of-the-art observations that you can get. At first with a node, but within 2-3 years, you're going to have a network. And yeah, who to contact. So anybody, set a group. And just to remind you, there is one evening meeting in 2 weeks, and this is where we're first going to discuss the type of time allocation. So we want to have an idea of what things people might propose for. This is a web page. I'm just to show you the web page. If you want any more information, you can either go here or you can talk to anybody. So that's it.
Time for some questions.
So I missed one point. I don't know if you can mention, but what is the diameter of the telescope?
A meter.
The diameter, 1 meter.
Yes.
Okay. And another question I have is how much time will be available for general proposals?
So this is being decided. General proposals. The idea is that it's not going to be like general Spanish cat, because it's a dedicated telescope. So you can propose, but you have to have the...
No, but I mean for general proposal within the network. I mean, you can propose for weeks, months.
Well, it depends how exciting your project is. If they say that's great and you need 2 months.
Okay.
So it's open still. That's why they need to see all these test proposals before they decide how it's going to work.
Can I ask about the spectrograph? You give the resolution of the spectrograph, but what's the spectral range that's observed at any given time?
It's between 4.5 and 4 and 6. Sorry. Basically, this region here. 6.5.
Okay. Yes.
7,
Thanks.
sorry.
Thanks. And also, the basic projects, the seismological projects, what range of stellar types are contemplated?
The type of stars?
Yes.
So it's the ones that have solar-like oscillations.
Solar-like
Because
oscillations.
the amplitudes are tiny. And
Right. Right. So, O and B stars are obviously not contemplated in the main program. But if anybody wants to observe them, they'd have to propose. All right? Okay. Right.
Okay. More comments? Questions? Yes, we have to know.
Well, just to be the devil advocate for a few seconds, even for the Sun, the situation about asteroseismology is not so wonderful as we would like, because with the new solar abundances, we are really in trouble.
Yes, but that's a solar abundance problem. Not the hydroseismology problem. The hydroseismology. That's true. But there's certain things that you can isolate. So I showed examples of isolating some signatures using the frequency, so you can get the basic convection zone, you get the healing zone, you can get the convective regions, the sound speed jumps, you can get the global properties, you can test the equation of states, you can test the opacities. Yeah. But we will get there. We need something like this to get there. Because if we don't understand the sun, like, we need to know other stars. Sure, but we also, if we could observe things on other stars, at least you can see trends and put the sun into context. Maybe, hopefully we'll answer something about the sun.
Shall you comment something on the mini song?
Oh, mini sound. Okay. Okay. So this is basically from the Chinese. The Chinese decide they want to invest lots of money. So they're going to build one node and a second one for themselves to justify their own money. And they want to put in a lot of 50 centimeters or 1 meter telescopes. 40 to 50 centimeters spectrophotometry. And the first one they want to put here on right-beside the dog, basically. So you can have simultaneous photometry and spectroscopy at the same time. And of course, robotic, automatic. Thank you. The important point.
Yes. You mentioned 2-3 years for a global network, which is the measured strength for song to have a network and have continuous corrects.
More than one.
How optimistic is 2-3 years for a network? And in Asia, where are you planning to put the telescope? For a curiosity.
Well, network, I need more than one. Start off with, so not a node. To have the 8, no idea. The funding has been secured for 2. We're hoping for 3, and then, of course, as the network gets stronger, it will help the proposals for more money. So I don't think anybody really has an idea of that, like a realistic idea. But within 2 years, at least, 3 years, there'll be 2 telescopes. The position, exactly? I'm not sure. Sorry.
Okay, concerning the sites. In principle, first light for the prototype is scheduled to be this summer. Chinese people already start to build because it's to duplicate the instrument. Then, knowing the Chinese, how they work, one may guess that spring 2012, the second node should be on. Then remember that for the rest of the nodes, we are talking about to duplicate a prototype. It is not the same as to develop, conceive, etc. The second thing is that Orlagh showed a simulation on the science that can be done with 2 sites. I think this is one of of the clues. Okay, we can do many things with already two sites. And I would like just to comment about the problem of the helioseismology concerning the solar abundances. What you say is true. I mean, there is a problem. But if one goes back 20 years ago, back in '89, was the end of a historical long debate about the missing neutrinos of the sun. During the 80s and part of the 90s, your words were repeated in the sense that helioseismology has a problem. In '89, it was proof that, sorry, not 98 or 89. Yeah, I'm talking about the Kamiokande, the latest, the Japanese experiment. Yeah, but the whole point is that it was proof that the helioseismology was not wrong. What was wrong was the physics of neutrinos. Yes, that was that. No. The improved solar model is improved because of helioseismology. That's correct.
Where does the lucky imaging camera fit in the research topic? How much time will be devoted to that instrument? The total?
I think it's simultaneous. They'll have the lucky imaging work at the same time.
Okay, so you can be taking the spectra of a central object in the field and doing lucky imaging of the same field.
Debate. I think that they are not. I'm not so sure. No.
I think there's a percentage of it going one way and another percentage going the other way.
Okay. Any more comments? Yes.
These are all the details that we need to.
How are you going to achieve the radial velocity precision? Are you going to have an iodine cell or simultaneous calibration? Iodine cell. And how are you going? Is there already a plan to handle, guess what, target opportunity?
It's going to be discussed. This is why we need it.
But it's going to be discussed. There's no. All right. Very good.
You're getting excited.
Okay.
Other target of opportunities, because there is an important group behind on microwave.
Okay. Are there any more comments or suggestions?
Was microlensing the main reason to put in the lucky imaging camera, or what was the scientific reasoning for that one?
I think it was.
Then I think we have a very nice project, and if you have any more questions, you should talk to Orlagh and her collaborators, and we should thank her again, so please.